Hello everyone, and welcome to the extra slides that we will dedicate to understanding how we can improve language models with other ways that are different from the smoothing, the Laplace smoothing that we have inspected in the lecture itself. So let me move to the slide that we stopped at. So in the lecture we stopped at this slide in which we clarify that add-one smoothing is actually a blunt tool in order to perform improvements to the language model in order to address the words that have not been seen before. You are adding 1 to each count, and then you are dividing by grade count mass, and then you are retweaking the counts in order to account for the discounting that you have to incorporate for each word that does appear in the training test, to lend some of its count to the words that do not appear in the training test. So there are better ways to handle language models and words that have not been seen before other than the add-one smoothing. One way is that we can use backoff. Backoff essentially means, and I'm guessing that you still remember how backoff worked in previous contexts in previous lectures. It's basically using less context if the current context is not enough. So if you have trigrams, then use them. If trigrams prove to have good probability mass, then use them. If you don't have good probability mass for trigrams, just use bigrams. If not, then use unigrams. So basically you move in context one less step in the window in order to try and come up with a decent probability value for the word that should be generated. But a better technique is to use interpolation, which is basically mixing the unigram, the bigram, and the trigram models into one assessment of probability. Interpolation usually works better. So how does interpolation work? Basically what you have here is you have the probability of a word given a previous context. It could be any context with any length. Let's assume that it's the two words. So let's assume this is a trigram. So what is the probability of a word given the probabilities of the two words preceding that word? We will basically do the following. We will use the trigram probability, same as this one, and then the bigram probability, and then the unigram probability. This is the bi, this is the uni, and this is the trigram. But we will assign a weight for each one of the grams. Now, initial weights should sum up to 1. So you can just use roughly equal weights here. The lambdas could be equal. The important thing is that the summation has to be 1. However, you can actually change the lambdas weights that you want to assign depending on how information does the context hold for you. So for example, if this context has more information, then you should assign a higher probability for it. If this context has more information, then you can assign a high probability for it. Again, the condition is the sum of the lambdas have to be equal to 1. How can you tune the lambdas then? How can you come up with the good values of lambdas? So we have said before that we need to divide our data set into a training set and then a testing set, and from the training set you compute the probabilities, and for the testing set you compute the perplexity. What you can do in addition to that is that your entire data set could actually be divided into three partitions instead of two. So the first partition will be the training set. From that you produce the probabilities again, and then you use something that we call the held out set in order to fine tune the lambdas, which are the parameters that we have and need to find values for. So here you can just compute the probabilities. Here you can just compute the probabilities, and then you need to compute the lambdas. So you try to build a model here that will maximize this overall probability. So you will try different values of lambdas that will result in the highest possible probability of this trigram. How will you do that? You just use the information that you have in the held out data. Okay, so that will result in a method in which you can just interpolate all of these. But again, the probability computations will depend on the maximum likelihood estimates that you find in the data itself. How do you deal with very large corpora that are at the scale of the web, for example? It's basically very challenging to compute these bigram or unigram or trigram probabilities for all of the sentences that you can see. This is practically going to take a lot of time, because again, in order to compute it for the training data, you just need to do counts, and then for the counts you need to do divisions in order to produce the probabilities. And this will be very challenging, especially if you have a large number of n-grams with very low counts, which is usually the case on the web. So for web based corpora, you can actually use pruning as a method in order to make things a little bit more scalable. Here we are looking for scalability, not looking for accuracy really. So how do we do that? You only store the n-grams that have a count above a certain threshold. So you don't store all of the n-gram counts. Remember that matrix we have seen? I think we can actually call it here the comparison between the row counts and the normalized or discounted counts. So you can see that we are keeping these counts here in order to help us with the computation of the probabilities. So instead of keeping all of these counts, which as you can imagine could be a very huge matrix, if you have millions and millions of words, you can actually just do a count of the n-grams that have a count that is higher than a given threshold. Now you can say that this threshold could be 100 words, can be 500 words, can be 1000 words. However you want to set it, you just keep the n-gram counts that are larger than this threshold. You can also focus on the higher n-grams, like the 5 grams, 6 grams, 7 grams, and quadrigrams, for example, and just keep the ones that have a decent count, and just discard the ones that have a very small count or appear only once, for example. Or you can just use entropy, and entropy is another measure that has been introduced in information theory, which basically introduces the probability that a bigram will appear in text. The higher the probability, the lower the entropy, so you can just use entropy as a measure for pruning. You can also use efficient data structures, you can use efficient indices, and you can use Huffman encoding in order to store the data. These are techniques that do not really improve the language models themselves. They help you implement the language models on a web scale. There's another thing that will help you try to come up with a better language model for the web. Not exactly the most accurate again, but still something that can work for the web. So this is what we will call stupid backoff. It's something that is used for language models that depend on web scale corpora. So basically the concept is do not discount. Instead, just do a stupid backoff using a fixed value of weight or score, if we might say, that you give for the model to which you back off. So this basically is the stupid backoff. If you want to compute the score, that's why we use the word S now, the letter S and not the letter P, because here you cannot actually produce a probability anymore. So this is the score of the word given the words in a previous context, this previous context, which is I minus K plus 1. This is the previous context. However you want to set it. It's a trigram, quadrigram, bigram, whatever. So the score of a word given the previous context, the previous words in the context, is going to be computed as the count of the word plus the context divided by the count of the context, which we have seen earlier in the probability that we have computed in the lecture. But we will only use this if the count itself of the word plus the context is larger than 0. If the word does not appear in that context, you back off to the previous context. So basically what you do is you use the context of the word, the probability of the word, given a smaller context. So if you are using the trigram, use the bigram. If you're using the bigram, then you use the unigram. If you're using the quadrigram, then you use the trigram, okay? But then this is the score that you will compute for this word using the lesser context or the smaller context, and then you multiply that by a fixed value, which is 0.4. And if you fall back to the unigram, you just compute the count of a word over the entire size of the corpus, or the number of words that appear in the corpus. So again, if you want to compute the score of a word given a context, let's assume this is a trigram context, then you basically compute the word plus after 2 words and divide that by the count of the 2 words, the preceding context. This is the context. So if you want to compute the probability of the word glasses, given the words reading, use, then you compute the number of times this sentence as a whole appears, then you divide it by the number of times use reading appears. If this number of the trigram is larger than 0, then you can use that. If the number is not, if there's no incident in which the word glasses appears after reading use, then you fall back into a smaller window, which in that case is going to be the bigram. So here you will have to compute the number of times glasses appears after reading divided by the number of times the word reading itself appears. Now the context is much smaller. And then you multiply that by 0.4 because you want to give less weight to that lesser context, because it ignores some of the useful information that you may have produced using the trigram itself. This stupid back-off scheme is what is used for generating language models on the web scale. There are also advanced smoothing algorithms that are highly sophisticated, such as the Goat-Turing, the Kneser-Nye, the Witten-Bell, and the intuition is also discount, such similar to what Add-1 smoothing or Laplace smoothing does, but you will discount in such a way as to optimize the performance of the discounting mechanism itself. You don't have to discount differently for each word, and in addition try to use as much context as possible if you interpolate. From these 3 methods, I have chosen the Kneser-Nye because it's the one that is most used now in the context of language models. So let's try to understand what Kneser-Nye actually, how it works. Here we will take a look at the absolute discounting interpolation using Kneser-Nye, and you will see that what is being used in reality is actually a different version of this absolute counting. The concept is, instead of having to perform a separate discounting factor for each word, such as the one that we have seen here, let me again recall that slide in which we compare. I'm trying to find the comparison slide here. Yes. As you can see here, each count in the bigram, counts that we have used to illustrate how the Add-1 smoothing works, has been discounted differently. So you can see that some of the zeros are counted, are incremented more than others, and you can see that some of the non-zero values have been discounted more than others. What Kneser-Nye says is that I will not do that. I will just use a fixed discount value. And the fixed discount value is going to be 0.75. So for all the words that have non-zero counts, I will just discount them by 0.75. How did they come up with this value? It was the result of the good Turing smoothing, which discovered that using a fixed discounting value is much better, more efficient, and produces roughly better results than what add-one smoothing does. Okay, so now we need to compute the probability discounted, the probability of the probability of a word given the previous word, but we want it discounted. So it is essentially the count of the word preceded by this previous word or this previous context divided by the context. Again, we will always keep referring to this as a context. But then we will discount this by a fixed factor here. We will not add this factor to the denominator like what we have with the add-one smoothing, but we will make up for it in the interpolated addition here to the discounted probability. So here we will interpolate with the unigram. This is the bigram. So we will interpolate with the unigram. And we will interpolate and multiply this interpolated unigram probability by the lambda factor. And this lambda factor is essentially a weight. And since we said that the lambda will have to sum to 1, but we don't have more than one lambda here, what we will do is that we will assign a weight to this lambda that will take into consideration the discounting that we have made here and the possible additions to the counts that should have been made in the denominator. So lambda in effect will be a function of the discounting that it's going to be a normalization of the discounting that we have made. Okay. So let's take a closer look at this discounting and this interpolation with the unigram policy that we use for the Kneser-Nye. Kneser-Nye actually does not use the unigrams. Kneser-Nye says that unigrams do not usually hold a good amount of information that we can rely on for meaningful interpolation. So instead of the unigram, what will Kneser-Nye use? It will actually use a different form of the unigram. Still going to be the unigram, but it's going to be a different form. But first we need to understand the rationale behind the Kneser-Nye smoothing scheme not using the raw unigram. So again, let's refer to the Shannon game of word completion. Let's inspect this example. I can't see without my reading, and then you need a word to complete the sentence. You probably, as humans, know that the word that will most complete the sentence is the glasses word. I can't read without my reading. I can't see without my reading glasses. However, if we use the row unigrams, they basically are established based on the probabilities of the words. Now, the probability of the word glasses is low. The probability of a word such as Francesco, for example, in a given corpus is going to be very high. So compared to glasses, the word Francesco would appear more. So since it appears more, it has a higher unigram probability. So it's going to be used here to complete the sentence in which you have reading. What is the next word that should follow? Reading my. But we can't use the word Francisco because it disrupts the whole meaning of the sentence. How can we avoid that? We have to use context of the unigram again. So here we are using only the context for the word that we want to inspect as the word that we need to use for completion. But if you use the unigram, you need to inspect first the probability of this unigram appearing in other contexts. So here you have two words that may be used, glasses and Francisco. Now, if we leave the unigram probability as is, most probably you will have a high probability for Francisco and a low probability for glasses. But if you use the context in which Francisco appears and the context in which glasses appears, regardless of the current context that we are trying to investigate, which is reading. Now, this is our current context. Okay? But we now need to investigate the overall context in which the two words appear, Francisco and glasses. This is just for the example, but the same methodology will apply for all of the words that we need to investigate in order to see if they complete a given sentence. So how do we compare the contexts of both words, glasses and Francisco? And how do we determine which one gives us a context that we can actually use? What we will basically do is we will check glasses and see how many contexts does it complete. And we will also check Francisco and see how many contexts does it complete. Both for entire corpus. And as you can see, glasses here can appear after many words. Again, the preceding word is what we will call the context. So the word glasses in general, without referring to the specific word reading, here, for example, we have reading as the previous word, and we want to see whether glasses or Francisco have higher probability. So as you can see, the count of the word with the previous word could be very low, could be decent, but the count of the previous word, which is glasses or Francisco, could be higher for Francisco than it is for glasses. So here, what we want to do is, we want to see the word glasses and how many words does it appear after, how many contexts does it complete. This is essentially it. Glasses appears after how many words exactly? How many contexts does it complete? And we will do the same thing for Francisco. How many words does Francisco follow? How many contexts does Francisco complete? And as you have guessed already, Francisco only appears after the word San Francisco. Okay? So here, the word Francisco does not complete many contexts. It actually appears only after one word. Whereas the word glasses appears after ring, appears after other words with a fairly higher probability. So we don't want to measure the number of bigrams that glasses appears in. We just want to measure how many words does glasses appear after. And here also we want to measure how many words does Francisco appear after. And checking or inspecting these numbers of words that make the context of glasses or Francisco, finding that Francisco constitutes a much smaller context, then it will be given a lesser weight, and hence it will not overwhelm the unigram value here. So the Kneser-Nye reformulates the unigram probability as a probability of novel continuation. How likely is a word W to appear as a novel continuation after a context? So basically this is it. This is the number of times a word such as Francisco appears after a given word such as Sam. So here is the count of words preceding Francisco. And here is the count of all bigrams, all bigram types. Here is the count of all bigram counts. So out of all combinations of words, not counts of row bigrams, it's just the types of bigrams that appear in the text. So how many types of bigrams appear? And out of those, how many times does the word Francisco appear after another word? How many words does the word Francisco appear after? And this is what we will call the probability of continuation. So to reiterate, this is the number of contexts leading to word under inspection, of course, for unigram. And this is count of all bigram types. And this will be the probability of continuation that we can use to substitute the unigrams. Now we don't have the unigrams anymore. We just have the probability of continuation multiplied by the lambda, the weight. And then we have here the count of the word given the previous word. This is the bigram count. And here we have the count of the previous word, or what we refer to as the context. And of course, I want you to imagine that this could definitely be mapped to larger n-grams. So you can use it for trigrams, you can use it for quadrigrams, you can use it for higher order n-grams, no problem, because you will always use the continuation in the same way. And this is the discount factor that we have talked about. It's usually 0.75. What is left for us is to understand how the lambda itself is computed. Because I don't have the equation of the lambdas, I'll try to remember how it's computed. So the lambda here, let's clear this. The lambda here will be equal to the discounting factor that we have made, which is the count of the context, the discount value, which is 0.75, as we said, divided by the count of the context. So it's basically this part. And then we multiply that by the count of the context itself. So this is the count of the number of words that appear after this context, as long as it is larger than 0, of course. This is the count. This is the count of the number of words that appear as a context here. So how many times does this word or this context complete? How many words does it complete? How many words does it appear before, if we can say that? Okay, so that is not exclusive to the word we are trying to compute the probability for. So for example, let's refer to the other example that we have seen. So the word Sam, how many, the word reading that we have seen here. Let's go back to this example. So basically, we have seen that the continuation is the how many words does glass appear after? How many words does Francisco appear after? So here, in order to compute the lambda, we will have to check reading, because reading is the preceding word. So basically here, you are saying how many words, how many words does reading appear before, or lead to, or is the context of. It could be glasses, it could be reading book, it could be reading lecture, it could be whatever. So how many words does the word reading lead to? Multiply that by the discounting factor divided by the context that we are investigating, which is reading itself. How many times does reading appear in the corpus as a whole? So basically, if you take a closer look at this, and let me try to clean it again and rewrite it, the lambda will be equal to the D divided by the count of the preceding word in the context, multiplied by the number of words the count, let me just erase it and write it clean, the count of this context and all the words, as long as it is larger than 0, because you don't want to multiply 0 in this value and then have a lambda equal to 0. So basically this is it. It's the number of words appearing after context. Okay, so basically it is as if we are normalizing the number of words here by the total number of the number of words after the context by the total context itself. And this is in essence how Kneser-Nye smoothing works. It provides a better understanding of the structure of the sequence, and it does not do aggressive discounting as what we have seen in add-one smoothing. So you can use add-one smoothing for text categorization or classification, but you can use Kneser-Nye for language modeling. And if you have web-like corpora, you can actually use stupid backoff and just do without it. In the next lecture, we will take a look at vector semantics and word embeddings, and we will start to inspect how deep neural network models can be used in order to generate sentences, language models, and perform other types of NLP tasks. Until then, I hope you keep safe and sound, and I'll see you in the next lecture. Goodbye.